Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for May-June 2020 variant 1. So let's get started. Question 1 says an aeroplane of mass 2.5 times 10 to the power of 5 kilograms lands with a speed of 62 meters per second on a horizontal runway at time t equals 0. The aeroplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6.0 meters per second at t equals 35 seconds. Part AI says calculate the deceleration of the airplane in the 35 seconds after it lands. We have acceleration is equal to v minus u over t. So the acceleration is equal to 6.0 minus 62 divided by the time 35. That gives an answer of negative 1.6. So the deceleration is positive 1.6 and the unit is meters per second squared. Part I says the resultant force acting on the airplane as it decelerates, so we can use F is equal to ma, and we already have the acceleration, so we multiply 2.5 times 10 to the power of 5 kilograms by the acceleration 1.6. That gives an answer of 4.0 times 10 to the power of 5 newtons. I says the momentum of the airplane when its speed is 6.0 meters per second, so momentum is equal to mass multiplied by the velocity, and the mass is 2.5 times 10 to the power of 5 again, and we multiply that by 6.0 meters per second. That gives an answer of 1.5 times 10 to the power of 6, and the unit is kilograms meters per second, or we can write it as newtons second. Section B says at t equals 35 seconds, the airplane stops decelerating and moves along the runway at a constant speed of 6.0 meters per second for a further 15 seconds, so until time is 50. On figure 1.1, sketch the shape of the graph for the distance traveled by the airplane along the runway between time equals 0 and time equals 50 seconds. You are not required to calculate the distances or the values of the distances. So starting with deceleration, that means a decreasing slope or a decreasing gradient, so a curve becoming more horizontal. And then constant speed will mean constant gradient, so it will be a straight line with the same final gradient of the graph we've drawn. So it will look like this. Part C says as the airplane decelerates, its kinetic energy decreases. Suggest what happens to this energy. We can say kinetic energy is converted to sound and heat as wasted energy. Question 2 says figure 2.1 is the extension load graph for a light spring S. We have the extension in centimeters and the load in newtons. State the range of loads for which S obeys Hooke's law. So that would be until the end of the straight line. So from 0 to 8.0 newtons, which is at this point on the graph. Part B says using information from figure 2.1, determine the spring constant K of the spring. So K is equal to the force divided by the extension. We can go on the graph and choose a force, for example, the 8 newtons. We can see what extension that gives on the y-axis. In this case, it's in the middle between 10 and 20. So this is 15 centimeters. And then we divide the force 8 divided by the extension 15. That gives an answer of 0.53 recurring, so it's approximately 0.53, and the unit here is newtons per centimeter, since the extension on the graph was in centimeters. Part C says a second spring identical to spring S is attached to spring S. The two springs are attached to a rod as shown in figure 2.2. A load of 4 newtons is suspended from the bottom of spring S. The arrangement is in equilibrium. State the name of the form of energy stored in the two springs when they are stretched. That would be elastic or strain energy. I says determine the extension of the arrangement in figure 2.2. So going back to the graph here, for 4 newtons, one spring has an extension of 7.5. So we say if one spring has an extension of 7.5, two springs in series would have an extension of double that, so the extension is 15 centimeters. So this is the answer. I says the load is carefully increased to 6 newtons in total. Calculate the distance moved by the load to the new equilibrium position as the load increases from 4 to 6 newtons. Again, going to the graph. So here we can just use cross multiplication. If from 0 to 4 newtons gave an extension of 15 centimeters, from 4 to 6 newtons, which is 2 newtons, This is half the force, so this would give half the extension, or we can just do cross multiplication. 2 times 15 over 4 That gives an answer of 7.5 centimeters. Question 3 is about manometers, so you can skip this question for the new syllabus. It says figure 3.1 shows gas trapped in the sealed end of a tube by a dense liquid, and there is a scale in centimeter cubed. The scale marked on the sealed end of the tube is calibrated to read the volume of gas trapped above the liquid surface. Figure 3.1 shows that initially the volume V1 of the gas is 60 centimeter cubed. The pressure of the atmosphere is 1.0 times 10 to the power of 5 Pascal. State how figure 3.1 shows that the pressure of the trapped gas is equal to the pressure of the atmosphere. So it is at the same height on both sides, and one exposed to the gas and one is open to the atmosphere. So this is the key here, that the levels of the liquid are the same on both sides. Part B says, explain in terms of the momentum of its molecules why trapped gas exerts a pressure on the walls of the tube. We say first that gas molecules move randomly and collide with the walls, and then we say that the change in momentum as they rebound exerts a force over the area of the wall. So pressure is equal to force divided by area. Section C says more of the dense liquid is poured into the open end of the tube. The level of the liquid surface in both the sealed end and the open end of the tube rises as shown in figure 3.2 below. The temperature of the trapped gas and the atmospheric pressure both remain constant. So we have a change in volume and pressure without a change in temperature. Part I says in the sealed end of the tube, the volume V2 of the trapped gas is 50. It was 60. In the open end of the tube, the liquid surface is 15 centimeters above the new level in the sealed tube. Calculate the new pressure P2 of the trapped gas. So we have an initial volume and a final volume. We have an initial pressure and we want to get a final pressure. So we use P1 V1 is equal to P2 V2. P1 was 1.0 times 10 to the power of 5 from the previous page, and the volume was 60, also from the previous page. P2 is the unknown here, and V2 is 50. So we divide the left-hand side by 50. That gives an answer of 1.2 times 10 to the power of 5 pascals. Double I says calculate the density of the liquid in the tube. We have the difference in pressure causing a difference in height 15 centimeters. We can say that the difference in pressure is equal to rho g delta h, which is the difference in height. And the difference in pressure between the gas and the atmosphere is 1.2 times 10 to the power of 5 minus 1.0 times 10 to the power of 5. So this is the gas and this is the atmosphere. And this is equal to the unknown density multiplied by g 9.8 multiplied by the change in height or the difference in height, which is 0.15 meters, not in centimeters. We have to convert it to meters by dividing by 100. And then we divide by this bracket on the left side. This gives an answer of 13,605.4, which can be approximated to 13,600 kilograms per meter cubed, which is the SI unit for density. Question 4 says water has a specific heat capacity of 4,200 joules per kilogram degrees Celsius and a boiling point of 100 degrees Celsius. State what is meant by the boiling point. It is the temperature at which liquid turns into gas. Part B says a mass of 0.30 kilograms of water at its boiling point is poured into a copper container which is initially at 11 degrees Celsius. After a few seconds, the temperature of the container and the water are both 95 degrees Celsius. Calculate the energy transferred from the water. So we can use the equation Q equals mc delta theta. And we have the mass 0.30, the specific heat capacity 4,200, and the change in temperature is the difference between 100 and 95. For boiling water, the boiling temperature is 100. This gives an answer of 6.3 times 10 to the power of 3 joules. Double I says calculate the thermal capacity of the copper container. So for thermal capacity, you use equation Q equals C delta theta. So C is equal to the energy divided by the change in temperature for the container. The energy is still the same, 6.3 times 10 to the power of 3. And the change in temperature for the container is the difference between 95 and 11 degrees Celsius from the question here. This gives an answer of 75 joules per degree Celsius, since we divided energy by change in temperature. Triple I says water from the container evaporates and the temperature of the remaining water decreases slowly. Explain in terms of molecules why evaporation causes the temperature of the remaining water to decrease. We can say that the most energetic molecules at the surface escape, leaving the rest of the molecules at a lower average kinetic energy. We can also mention that the molecules escaping absorb energy from the other molecules to break intermolecular forces. Question 5 says the distance between the center of a thin converging lens and each principal focus is 5.0 centimeters. Part A says describe what is meant by the term principal focus of a thin converging lens. We can say that it is the point where rays parallel to the principal axis or perpendicular to the lens meet after passing through the lens. So after the lens, they all meet at one point called the focus point. Part B says the lens is used as a magnifying glass to produce an image I of an object O. Underline the terms that describe the nature of the image produced by a magnifying glass. So it is always enlarged when used as a magnifying glass. It is not real, it is upright, and it is also virtual. Double I says figure 5.1 is a full-scale diagram of the lens and the image I, and we have every 5 small squares on the grid represent 1 centimeter. We are required to mark both principal focuses and label each of them F and draw on figure 5.1 to find the position of the object O and add the object O to the diagram. So first, the focus and the focal length was 5 centimeters. So until this point, this is 2, 4, and this is 5 centimeters. So this is the first focal point, and we remove the other markings. We go through the same distance on the other side to mark the other focal point. And as for the representation of the rays, there is a ray that goes through the optical center from the object towards the image without any bending. So we draw this one from the tip of the arrow to the optical center at the center of the lens and extend that line. And we know that this image is formed as a virtual image. So actually there is part of this ray that is an extension, and the ray is actually moving in this direction. As for the other ray, it must intersect with the top of the image also, but it is coming from the focal point, and it is the focal point on the other side of the lens since the ray is going to the right. So we connect the image with the focal point on the right, and the ray is going in this direction. And from this point, we are supposed to draw a horizontal ray that is parallel to the principal axis. So we have to make sure that the ray is actually horizontal until it meets the other ray. So these rays meet at this point. So this is the source of the rays. So the first one is going parallel to the principal axis, and from the center of the lens, it goes toward this focal point. And the extension is beyond the lens from the other side, going to the image. And the other ray is going through the optical center and without bending goes through the lens. And the rest is actually an extension also through the other side of the lens. And these rays come from the top of the arrow or the head of the arrow of the object. So we draw a vertical line and we draw the head of the arrow and label the object. It was called O, so we label this O. Part III says using figure 5.1 determine the distance of the object O from the center of the lens. So that would be according to your drawing. Not all people will draw the same exact drawing, but you should have approximate equal distances. So we have from this point to this point 5 squares, that's 1 centimeter, now 2 centimeters, now 3 centimeters. I'm going to write it to two significant figures, 3.0 centimeters. Question 6 says the speed of sound in air is 340 meters per second. A says calculate the range of wavelength for sounds that are audible by a healthy human ear, which can hear from a frequency of 20 Hz to frequency 20,000 Hz. So we can use the equation wavelength is equal to the speed over the frequency, and we calculate two wavelengths, once with the frequency, the minimum frequency 20, and once with the maximum frequency, which is 20,000. So the first one gives an answer of 17 meters, and the second one gives an answer of 0.017 meters. Part B says sound waves are longitudinal waves. Describe how a longitudinal wave differs from a transverse wave. We can say in longitudinal, the displacement or the vibration is parallel to the direction of energy transfer or direction of travel of the wave. And in transverse, the displacement or the vibration is perpendicular to energy transfer. Section C says figure 6.1 shows a band in front of a building. The drum produces a low frequency sound. Other musical instruments produce a high frequency sound. These sounds are equally loud. A young man at the side of the building hears the drum but not the high-frequency sounds from the other musical instruments. This means that some sounds can go around the corner here and some sounds cannot go around the corner and move in a straight line. This is about diffraction. So explain why this happens. We say that diffraction is better when size of gap, or the opening through which the wave passes, is close or smaller than wavelength. So longer wavelength can diffract around the corner of the building. Or we can say that short wavelength and high frequency cannot diffract around the corner of the building. Question 7 says an electromagnet consists of a solenoid X that is made of a copper wire. The solenoid contains an iron core. Explain why. First, the structure of copper makes it suitable for the wire. We can say that copper contains free electrons, which makes it a good conductor or good conductor of electricity. Double I says why iron is a suitable material for the core of an electromagnet. We say that iron is a soft magnetic material that can be magnetized and demagnetized easily. Part B says figure 7.1 shows the electromagnet inside the second solenoid Y. We have the terminals Y connected to an output, and we have the terminals of the solenoid Y connected to open terminals and solenoid X connected to an AC power supply. Section I says describe and explain what happens in solenoid Y when solenoid X is connected to an alternating current power supply. We say that the AC in solenoid X creates a changing magnetic field, and the change in flux in solenoid Y induces an alternating EMF or voltage. Double I says a switch and a lamp are connected in series with the terminals of solenoid Y. When the switch is closed, the lamp lights up at normal brightness, which means there is current now. Describe and explain what happens to the current in solenoid X after the current flows in solenoid Y when the switch is closed. So this is talking about Lenz's law, that the induced current opposes the change in flux that is causing the current. So we say that the current in X decreases since the induced current opposes the change in flux. Question 8 says the power supply used in an electric vehicle contains 990 rechargeable cells, each of electromotive force 1.2 volts. The cells are contained in packets in which all the cells are in series with each other. The EMF of each packet is 54 volts. Calculate the number of packets in the power supply. So we can get the number of cells in one packet or one pack. That would be 54 volts divided by 1.2 volts. That gives us 45 cells. And then we can get the number of packets by dividing the total number of cells, which is 990, by the number of cells in one packet, which is 45. That gives an answer of 22. Part B says when in use, each pack supplies a current of 3.5 amperes. Calculate the rate at which each cell is transferring chemical energy to electrical energy. So rate of transferring energy, that is actually power, and we can calculate that by multiplying voltage and current. So the voltage of each cell is 1.2 and the current is 3.5. That gives an answer of 4.2 watts. Double I says the packs are connected in parallel to supply a large current to drive the electric vehicle. Explain why it is necessary to use thick wires to carry this current. We can say that thick wires have low resistance and this decreases the heating effect, so the wires do not melt and there is less energy lost in the wires. Question 9a says describe how a digital signal differs from an analog signal. You may draw a diagram. So for digital, it has discrete values for the signal. As for analog, it varies continuously or can take any value. And we can draw a diagram for the digital signal as squares of high and low voltages like this, like a ladder, and we call it digital. And we can draw another diagram for the analog as a continuous curve and label it. Part B of this question is about logic gates, so you can skip it for the new syllabus. Part I says in the appropriate box, draw the symbol for an AND gate and the symbol for an OR gate. So for an AND gate, the symbol looks like this, and we have two inputs and one output. As for the OR gate, it looks like this, and we also have 2 inputs and 1 output for the gate. Double I says state how the behavior of an AND gate differs from that of an OR gate. We can say that AND only gives output 1 if both inputs are 1, and for OR gate gives output 1 if any of the inputs is 1. Question C says an arrangement of logic gates A, B, and C is shown in figure 9.1. The arrangement has 2 inputs X and Y and 2 outputs P and Q. Output P of logic gate B has a logic state 1, which is high. Determine the logic states of the 2 inputs of logic gate B. So this is a NOR gate, and we have an output 1, which should be 0 from an OR gate, not a NOR gate. So 0 from an OR gate only happens when both inputs are 0, so both inputs here are 0 or low. Double I says determine and explain the logic state of output Q. Going back to the diagram, A here acts as a NOT gate, and we have the output from the NOT gate 0, so X is actually 1 and then inverted to 0 by the NOT gate, and 0 is coming from Y, so we have 1 and 0 going to an OR gate at C. An OR gate with inputs 1 and 0 would give an output 1, but an OR gate would give an output 0. So we say now that A acts as a NOT gate, so X is equal to 1 and Y is equal to 0. And then we say that through a NOR gate, 1 and 0 produce 0. So Q is 0. Question 10 says figure 10.1 represents a neutral atom of an isotope of element X. State one similarity between this atom and the neutral atom of a different isotope of element X. So we have same number of protons in the nucleus and same number of orbiting electrons, since the positive charge is equal to the negative charge and all isotopes have the same proton number. Part B says the isotope of element X is radioactive. It decays from an isotope of element Y by emitting a beta particle. First, I says using figure 10.1 deduce the nuclide notation for the isotope of Y produced by this decay. So first we get the nuclide notation of X. We have 5 electrons on the outer shells, so there is 5 protons in the nucleus, so we have 5 dark circles representing the protons, and the white circles represent the neutrons, so we have 8 neutrons. So now we say for X, the nuclide notation, X has 5 protons and a total of 5 plus 8 nucleons, that is 13. And then we represent that by the nuclide equation. A beta particle has numbers 0 and -1. So Y must have the same nucleon number, which is 13, and a proton number of 5 plus 1, which is 6. So at the top here we have 13, and at the bottom we have 6. Part double I says beta particles ionize the air. They pass through less strongly than the same number of alpha particles. Suggest why this is so. We can say that beta particles are much lighter than alpha particles and that they have smaller charge. Also, we can say that beta particles travel much faster than alpha particles. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.